Welcome to today's explainer on X-Ray Photoelectron Spectroscopy, or XPS. I'm your host, Dr. Chem. Now, I want you to imagine for just a second that you're a detective. But instead of investigating a normal macroscopic crime scene, you're tasked with uncovering a really high-stakes mystery, right at the absolute limits of physical reality. You need to know exactly what elements are hanging out on the very surface of a material, and you need to know exactly how those atoms are chemically bonded to one another. Well, today, we're exploring the ultimate tool for that kind of microscopic detective work. In this session, we're going to cover the principles, the instrumentation, how it all actually works, spectrum interpretation, and of course, the real-world applications, advantages, and limitations of XPS. It is honestly one of the most important surface analysis techniques we have in modern chemistry, material science, and nanotechnology. Here's a quick look at our agenda for today. We've got 1. The atomic detective, 2. The photoelectric effect, 3. Inside the XPS instrument, 4. Decoding the spectrum, 5. The X-ray family tree, and 6. Real-world applications. All right, let's jump right in. Section 1. The atomic detective. Probing the surface. Let's start by getting absolutely clear on what we mean when we call this the ultimate investigative tool. X-ray photoelectron spectroscopy, XPS, is an extraordinarily surface-sensitive analytical technique. We use it to figure out not just the elemental composition, like what atoms are there, but also their specific chemical states and their electronic environments. And here's the kicker. XPS analyzes only the top 1 to 10 nanometers of a sample. We are talking about just a few atomic layers deep. So this technique isn't about what's going on deep inside the bulk of a material. It is entirely focused on what is happening right at the boundary, where that material interacts with the rest of the world. To really appreciate XPS, we need to lay out its core capabilities and, a few of its constraints. As we said, it probes just the uppermost 1 to 10 nanometers, making it incredibly precise. Now, it acts as a virtually universal elemental detector. It can spot pretty much every element on the periodic table, with 2 exceptions: hydrogen and helium. Those 2 are just too light and simply don't produce measurable photoelectron signals under normal conditions. But for everything else, it's amazing. Plus, it gives us quantitative analysis without needing external standards. That means we can estimate relative atomic concentrations straight from the data. And it pulls all this off with detection limits ranging from about 0.1 to 1%. Not too shabby, right? Section 2, the photoelectric effect, Einstein's Nobel Prize-winning physics. The entire foundation of this high-tech machinery actually relies on a phenomenon that Albert Einstein formalized way back in 1905. It's the very breakthrough that won him the Nobel Prize in physics. Let's break down exactly how this photoelectric effect plays out during an XPS scan. Step 1, we blast our sample with high-energy X-rays. Step 2, an electron, just sitting quietly down in an inner atomic orbital, absorbs the energy of an incoming X-ray photon. Step 3 is where the magic happens, the dramatic escape. That energized electron, which we now call a photoelectron, gets forcefully ejected completely out of the atom. Finally, in step 4, our XPS instrument catches that escaping electron and precisely measures its kinetic energy. Okay, so this fundamental equation right here is absolutely crucial. The binding energy of the electron is equal to the incoming photon energy minus the measured kinetic energy minus the spectrometer's work function. It's simple math, really, because we know the exact energy of the X-rays we're firing at the sample, and our instrument is measuring the kinetic energy of the electron as it flies away. We can just solve for the binding energy. And that binding energy tells us exactly how tightly that specific electron was being held by its parent atom. If you want to picture it visually, think of the incoming photon energy as the driving force. It's pushing the electron all the way up and out of its bound state. The kinetic energy? Well, that's just whatever energy is left over once the electron actually breaks free and clears the spectrometer's work function. Now, since every single element on the periodic table holds onto its electrons with a very specific, unique amount of force, that resulting binding energy acts like an unmistakable atomic fingerprint. You find the binding energy, you identify the element. Pure and simple. Section 3. Inside the XPS instrument, the electron's journey. Let's look at the actual hardware and follow the electron's journey. Down at the X-ray source, usually firing aluminum or magnesium K-alpha radiation, the sample gets bombarded. As those photoelectrons are ejected from the surface, they travel up through a series of extraction lenses. You can think of these lenses as a highly specialized funnel, carefully guiding and focusing the electrons into the energy analyzer. The analyzer separates them out based on their kinetic energy, And finally, they smash into a multi-channel detector at the end of the path, where all that beautiful data is recorded by the computer. But there is a massive catch to making this whole thing work. This entire journey has to happen inside an ultra-high vacuum. We're talking pressures between 10 to the -9 and 10 to the -10 millibar. Why such an extreme vacuum? Well, if these ejected electrons were to hit any stray air molecules on their way to the detector, they'd scatter. They'd lose energy, and it would completely ruin our measurements. Plus, remember how incredibly surface-sensitive XPS is? Even a single second of exposure to ambient room pressure would coat your sample in a monolayer of contamination. We absolutely need a perfectly cleared room to get accurate results. Section 4. Decoding the spectrum. Reading the fingerprints. So, our instrument has captured the electrons and the computer has crunched the numbers. Now we have to put our detective hats back on. Once we catch these escaping electrons and calculate their binding energies, how do we actually read their secrets? How do we determine the chemical states? What does this data actually look like? Well, an XPS spectrum is basically a landscape of peaks and valleys. The position of a peak on the horizontal axis, that's our binding energy, tells us exactly which element we're looking at. Carbon, oxygen, nitrogen, silicon, various metals, they all produce characteristic peaks at distinct, totally predictable addresses on this axis. Meanwhile, the area under the peak, its intensity, tells us the relative concentration of that element. So at a glance, it's this really elegant quantitative map of the surface chemistry. But here is where XPS truly flexes its muscles. It doesn't just tell you that an element is present, it tells you what that element is doing. You see, the binding energy of an electron changes just a tiny bit depending on the atoms surrounding it. We call these minute variations chemical shifts. For example, if a carbon atom is bonded to a highly electronegative atom like fluorine, the binding energy shifts noticeably. This is huge. It allows researchers to distinguish between completely different oxidation states. You can look at a piece of iron and definitively say, this part is pure metallic iron, but over here it's begun to form iron oxide. Rust. Section 5. The X-Ray Family Tree. The Precision Toolkit. Now, it is important to recognize that XPS doesn't exist in a vacuum. Well, okay, the instrument does, but the technique itself is part of a much larger, highly specialized family of X-ray characterization tools. You've got XRD, which uses constructive interference to figure out crystalline phases. There's EDS, which fires high-energy electrons to stimulate X-ray emission. SAX looks at particle size and shape, and XAFS tunes into specific absorption edges. Those are all brilliant, amazing techniques, but they largely look at the bulk of a material. When you need extreme surface sensitivity, when you only care about those top 1 to 10 nanometers, XPS remains the undisputed king. Section 6. Real-world applications. From micro to macro. All right, let's explore why all this atomic-level physics actually matters in our daily lives. Take a look at this. When researchers are studying something like a tantalum oxide film, they can use a gentle ion sputtering gun right inside the XPS chamber to slowly etch away the uppermost layers of the material, taking XPS measurements at every single step. It's literally like peeling an onion at the atomic level. As the oxidized layers are sputtered away, the pure elemental tantalum underneath is finally revealed. This exact capability is absolutely vital for designing and characterizing the incredibly thin films used in the semiconductor devices powering the smartphone or computer you are using right now. Because surface properties entirely dictate how materials interact with their environment, XPS applications are just everywhere. In nanotechnology, researchers use it to characterize nanoparticles. In the semiconductor industry, it ensures the purity of electronic thin films. In catalysis, it maps out the active surface sites that drive critical chemical reactions. Environmental scientists rely on it to study trace pollutants. And in the medical field, XPS is critical for evaluating biomaterials. It's how we ensure that a titanium joint implant will correctly and safely interface with human bone and tissue instead of being rejected. Now, despite its immense power, we did mention that traditional XPS has a pretty strict limitation, that ultra-high vacuum environment. Historically, that basically restricted us to testing only completely dry, solid samples. But technology is always evolving. Enter NAP XPS, or Near Ambient Pressure XPS. By using these really clever differentially pumped lens systems, modern instruments can now operate at pressures up to 25 millibar. This is a massive game changer. It finally allows scientists to analyze semi-volatile liquids, outgassing materials, and even real-world biological samples in conditions that closely mimic their natural environments.
To sum it all up, X-ray photoelectron spectroscopy is a truly indispensable tool. Building off Einstein's photoelectric effect, it gives us unparalleled insight into the microscopic chemical world. Its ability to provide quantitative, chemical state data from just the outermost atoms shapes everything from the chips in our electronics to the life-saving implants in our bodies. So I'll leave you with this thought. If you had an XPS machine at your disposal and you could peel back the top few nanometers of literally any surface on Earth to reveal its exact chemical fingerprint, what invisible secrets would you want to uncover first? Thank you for joining me for this explainer. Stay curious, everyone.